Hello again. Well, I hope you all had a good chat. I popped around and said hello to a few people. So I would now like to welcome Mahes Maheswaren from Water New South Wales to the stage. Mahes is going to give us an update of a number of things that Water New South Wales have been doing. So I can see you, Mahes. Feel free to share your screen and get into it. There we go. It's all working. I will disappear.
All working. Hi. I'm so excited to be in this new platform of sharing. Good evening, everybody. I'm Mahes Maheswaren from Water New South Wales. I manage multiple water modeling teams. So because of this compressed presentation, I thought of bringing in all the activities going in Water New South Wales so that all the other eWater users can share some knowledge both ways. So this presentation is first acknowledge all the contributors for this presentation. Soon I will be talking about the Mole new dam modeling that was done by Ashok Rao. He is the audience. And followed by Dunkovan dam modeling, which is done by Tahir Hamid. And then the next one was Wangala dam raising modeling going on. Gurmeet Singh was done that. And then few other projects on the Greater Sydney area with Ashok and Golam has done the work. And most of the other major excitement work was done in Bawan Darling in the recent past. That was done by Hemanta Perra and Gurmeet Singh. So all these people are in the audience today. You're all welcome to talk to them and share the knowledge both ways, exchange your knowledge. Importantly, all, I would thank all the eWater staff for their continued cooperation and the great leadership by Robert Carr on this great mission of building this eWater software platform. All right, the Water New South Wales
Mahes, I'll just jump in briefly and suggest that you put your presentation in presentation mode. It might be a bit bigger that way for others.
Is that good now?
Maybe.
Good now? Good? Okay.
Yeah.
All right. Thank you. So in the eWater modeling program, we have developed models for the purpose of infrastructure planning and also apply these models for operations. So basically, the program started 3 years back, and with almost now and 2 years back, we delivered a 20-year infrastructure option study using all these models. The models further used recently on all the New South Wales new dam proposal. There are 3 dam proposals which I will describe in a few minutes. And also we used this, and also we developed a model for Bawan Darling to link up all the valley models all the way down to Murray. And the Bawan Darling model was used for Western VS project. In that project, we have been looking at ways of improving water security for country town supplies. And also the models are operationalized in our real-time platform that's called CALM, Computer-Aided River Management System. In that, most of the model can be run automatically, and also every day the operational staff can make decision on how to release and the amount of released water, optimizing the supply, optimizing our releases. And also we use the source models to look at climate change impact for Greater Sydney area using within the new NARCLIM 1.5 data set. The significant features of the recent work is just most of our models are developed using Medbureau AWAP gridded rainfall and evaporation data as a primary input data set. That gives us lots of flexibility on development of the models. And also some of the models are proven to perform better with the gridded evaporation data set, and it was published in the conference back some years back. And also the river reach calibration had been also done now using the latest DEM data, and also using all the abstraction data along those river data sets. So the latest DEM data is now post-processed and used as a reach data set. And also later I'll describe there are some more advances on using remote sensing data also on top of the thing. The remote sensing data is usually used using indices to mark the water area and the crop area, and multiple maps are overlaid, and the boundaries are cut for farm dams, and the farm dams areas and the volumes are tracked through over the time. And also similar way we can track the crop development using some other indices, NDVI, using remote satellite data. For last 10 years, we could do fair bit of advanced tracking of crop development in multiple models. And also most of the eWater source model receive input from hydraulic models, and they provide hydraulic ratings and breakouts and things like that. And all the models incorporate current water sharing plan rules. And the most importantly, we have access to the system operational staff, and we discuss with them and bring up all their operational knowledge on top of the models. Basically, the screen shows how complex these models are, and starting from the top end of the border, and the border river has got very complex interaction with the Queensland water sharing rules, and also multiple complexities are there, and then followed by Guida, Namoi, and all these three models connected into the upper Darling model, and the Macquarie also connected to the upper Barwon models. And the Lachlan and Murrumbidgee has their own complexities, and they all developed in the last 2 years. And all these models provide input to the late Barwon and Darling models. I will describe that in a few minutes in the coming slides. In the border river, we have got a new dam proposed at Mole River, and it was proposed some time back. And the map shows the location of the Mole, the border river catchment and the Mole Dam. And this, so it has got 4 dams, and also complex water sharing rules across Queensland border, and also there are intergovernmental rules. All these complex rules are built in the source model. And the Mole Dam proposed to augment the supply options for the valley under federal and government water security improvement initiative. Is the slides are not moving? I hear that slides are not moving, so I had to go back, and should be okay now. Thanks, Tahir, for telling us, because slides doesn't move with the slide doesn't move with the full. All right, sorry, I had to repeat some of these things. This is the model structure of starting from the border river all the way down. And with the border river in the top, it has got all the complex rules, and the map is just shown on the screen now. Sorry for the small problem. And then I'll show I already described the screen, and the screen shows how all these models are interconnected all the way from border, all the way down to border, Namoi, Macquarie, and Lachlan. And then the Murrumbidgee and other models are shown down there. And the border river, the top end of the New South Wales, and the Mole Dam proposal is the circle at the bottom end on the map shown there. And in the border river, we have got all this complex water sharing rule, all built in the border river model. Ashok Rath is on the audience. If you have any questions on the border river, how we have looked at this, we can have discussion. Basically, what we have looked at is number of dam sizes and looked at what percentage of the time the different size dam is provide general security average volumes. So as you can see, after a certain big dam size, as shown on the graph up there, you can see the dams are, the size is not very effective. They are all coming closer. And also on the other side, the cost also goes up. So this is one of the simplest application of the source. In very fast way, we can evaluate the multiple size dams and come up with options. And also when we can look at other parameters like all the economics and also other environmental parameters downstream also. So, and the next one application was on the Dunkoven in the Peel, Dunkoven Dam in the Peel Valley. In the Tamsford town is supplied with this dam and is unable to meet. There's a small dam. In the last drought, we had a lot of trouble, and the government proposed to have raise the dam, make it bigger. And so the dam size versus yield graph was developed for multiple dam sizes and also multiple dam sizes and the environmental rules and all the other things looked through. We built a large dam for the country town supply. The full yield utilization will not happen immediately. And over the time, this reliability will increase significantly. And this modeling was done by Tahir Hamid. He's in the audience. If you want to understand how complex this work was, please talk to him. The next one was the Waingala Dam, which is in the Lachlan Valley. It was proposed to raise this dam, and that was found to be a better proposal than building a new dam further further down in the valley. And this was done in the Lachlan model. So, and that was done by Gurmeet Singh. He's in the audience, and there are the many ways in this work. He need to look at many metrics, and also need to look at inflow, the design inflows, and all this work was done by source, by automation, and a lot of scripting, and also looking at multiple environmental parameters. That's basically on the raising options. Modeling work was done by multiple options: dam raising, including operational scenarios, transolution rules, spillway options. All these multiple model runs were done in source model and processed. There are multiple hydrological metrics need to be extracted from the source model. And this source modeling platform provides very efficient way of running all these models in an automated fashion and produce number of data sets which can be analyzed. And also, particularly, the upstream inundation map also produced, and also using biodiversity modeling also done. And this work was done by Gurmeet Singh. He is also on the audience. You are welcome to have a chat with him on how we have done this work at a very short time frame. And the next one was integrating, linking up all these models. A model for source model was built for Bawan Darling, all the way from the Upper Darling model, start from Mangandai all the way to Wilcannia. And this model was very complex, and in this we have got number of weirs, around 20 weirs and 5 on the tributary. And there are other dams also, 2 dams on one of the tributary. And 47 irrigation users are there. They have got individually modeled in the source model. They have got 3 classes of licenses, And also we have got multiple country town supply along the river, and also stock and domestic supply. This model was done by Helen Fairweather. He's in the audience. And there are a number of things, advanced new things introduced in this model, mostly in the area of using remote sensing and also using flood models into the source model. Here what we have done is we have used latest Sentinel data to track the crop area cropped and for different farm dams, and also the volume of water in different farm dams by tracking the water surface area and also tracking a volume. And we could link that with those pumping volumes, and that's quite advanced work. And also this helped us to improve model the water losses as we move along. That's one of the very critical part of the boundary system, because river runs out of water, and to estimate the losses is very critical to have all these BAs accurately modeled, and the dead storage and all these BAs are quite important. And further down along this river, we also have developed a lower Darling source model, which is more complex because some of the operating rules for lake system is linked to the Mahes system, and which is another source model provide those rules across. And this model was developed by Gurmeet Singh, and this was used, both lower Darling and the upper Darling model used to look at the water security and options to raise the VAs to improve the water security for country town. This modeling work almost complete now, and some of the critical things are the setting up the hydraulic model interface is quite important. We have got flood models built for along the river that provided very important input for the reach calibration on the hydraulics travel time. If you can run the flood hydraulic models using all the DEM data, and we can calibrate the travel times and get those travel time and put it in the other source model so that it will predict the movements of the flow much accurate. And also we have got it provides a lot of other ratings and a lot of other input data which is needed for the source model. So the flood modeling together with all the satellite remote sensing make us to make a very good model for the lower Darling and the upper Darling, which is quite important for New South Wales. So currently, bringing up all these together, all these team members are probably there, all in the team, and I'm asking you all have an individual chat about the current challenges. Are now we are moving all these models to hot start into and also automation, and also some of the time steps and need to be changed. And also the hot start part is right now being built by eWater. And also the next step is we are improving these models in the Greater Sydney catchment for bringing water quality modeling. And there's a presentation tomorrow by one of my staff, Marlene, on the water quality modeling. That's another big project to link up all the models on the water quality all the way from the catchment all the way to Greater Sydney supply end. So it's a big modeling project. You can listen to that tomorrow. And currently, what we are working in multiple modeling areas. One of the big area is bringing all these models together with standards. And there have been always violation of standards, and sometimes it happens. So what we are doing is now hedging around, going back to all these models and make sure all the standards of development, validation, calibration, and the naming and the conventions are all adapted accurately. So that's quite an important step, and we are cleaning up all the models. Anything done fast forward moment, all done, now cleaned up back to accurate standards. That's one of the big challenge. And the next big thing is when you do thousands of runs and thousands of modifications over time, the provenance or the versions control, which was talked sometime back also in today, and how we are going to do that. And already the eWater training, eWater team is helping us to build this system, and already we have got other provenance system within the software side of the world to have a version control over the thing. After all, everything together, the independent review is the next big thing. Each of these models are independently reviewed at various times at various parts of the development, particularly by the experts in the eWater team. So, and they have been absolutely helpful for us to deliver such a colossal amount of work for New South Wales. It will be very useful for our clients or the customers who are using New South Wales water. And that leads me to the last slide. And thank you all for listening to me today. And I'm actually I have summarized all the other staff's work together in one presentation. Please feel free to ask any detailed question with any of them or communicate them individually. Thank you very much. Thank you all.
Thank you, Mahes.
Thank you, Trudy.
I think I found a question hiding away in the general chat. So if it's not appropriate, then we can answer it separately, but I think it might be. The question is how to integrate source model with the flood model to disseminate flood hazards. Is source applied for
it's the other way around? Sorry, I can answer that actually.
Okay.
We are using the flood model to improve the source model to do better breakouts and all that sort of thing. It's more the flood models are used and calibrated and validated for the flood. I can't use that. I can't read the question full actually for some reason.
Sorry, will I move my screen?
Sorry. Okay, how to integrate with the flood model to decimate the flood hazards. That's not the objective of this project. Actually, we are developing flood model to do that part of the work, and that's not the main intention. Actually, we use the flood models to inform the hydrologic model on the breakout, on improving all of our all losses and the travel time and the hydraulics part. So it's other way around, and we need to have accurate hydraulic model developed in the using the complex hydraulics part to solve the other problem of. That's the best answer I can give.
No problem.
Thank you for that. Thanks for the question.
Thank you. Well, I will say thank you for all the wonderful acknowledgement of eWater's support. And Gollum says great summary of all their work. There was one other question that I can answer. It's whether eWater tools are region specific or universal, and they are absolutely universal.
I'm pretty sure that universal.
Thank you, Mahes. I will now let you disappear into back to the floor.
Okay, thank you all once again, Trudy, for bringing onto this exciting platform to have a chat with a lot of friends around the table. And also thanks to all the people all people up there listening to me. Thank you.
Excellent.
Excellent.
Well, feel free to track Mahes down and ask him some questions. So I will now, we will change tact slightly, and I will invite Emma James from Sydney Water to the stage. Emma is going to share how she has used source modelling to support the Picton wastewater treatment plant licence variation. Hopefully she's on her way to my stage.
The slow speed of it all.
There you are. Yep. A little bit frozen.
Let's see if we can go. Yeah. Tell me when you can see that one. Hopefully that comes up for everyone. So it should read Picton treatment, reuse and discharge when you can.
It is there now. So I will
Excellent.
disappear
Sorry for
and
the
let you
delay
present.
timing on this end.
It's disconcerting.
Great. Excellent. Thanks everyone for the opportunity to present this work. We've spent quite a while on this project, and really glad to have had the source modelling tool to help inform our wastewater planning. And this presentation might be different to a few others in that what I'm wanting to communicate to you is how some people outside the source modelling community want to understand the results. They want to use them, and the kind of questions that they've asked me and the team that have been supporting this work. And there's a number of people who've been part of helping us on that. So basically, I want to explain to you the context and the challenge for the Picton sewage treatment plant, what we're doing there, and why we used source modelling, and then these questions around what planners and ecologists want to know out of our modelling. The Picton sewage treatment plant is a wastewater treatment plant for about 5 villages. So it's only less than 20,000 people that we service, and it's discharging to some really important little waterways. And I'll show you some photos of them because I can't resist. And 20 years ago, we started. We purchased a farm, which is an unusual thing for a water utility to do in Australia, in most, in Sydney at least. But that farm is used for reusing the water that we treat, growing crops, and then selling the fodder, the silage, to dairy and beef farms. So there's some photos there showing the configuration. And we discharge from one of our dams to a little creek called Stone Quarry Creek, and it's a tributary of the Nepean River. And it being a very small little creek, it has flow conditions that aren't always perfect for discharge. The rules that were put in place 20 years ago are that you wait for the flow in the creek to be a certain flow rate before you're allowed to discharge a certain proportion of that creek flow rate to the waterways. And this is just a photo of our treatment plant. So we've got the intermittently decanted aerated lagoons, and the treatment process has been upgraded recently so that we've got the capacity to treat as much water as we like. But our farm has not got any bigger. So that's where the challenge is for us in reusing the volume of water that we're being able to get through this treatment facility. So in terms of numbers, it's only 3 megalitres a day that's coming into the treatment plant, and about 2 megalitres a day that we can either reuse or discharge. So we've got this shortfall, and it's causing us some operational stress. And the EPA are concerned about us releasing more water to the waterways. And so we're trying to seek a change to our licence and try to understand the best way to manage this effluent, and looking to reuse some more water, but also discharge some more water. Just to give you some waterway shots, which is what all the modelling is trying to inform, how to protect this little Stone Quarry Creek with beautiful sandstone escarpment sort of edges to it in a deep valley. So really cool little terrain. We've got drone footage, which is really exciting. Some photos of the Nepean River now, so an area that's important for recreation. There's a threatened dragonfly that's only found in a few spots, and a really nice sort of part of the world. And so one of the options is to start thinking about discharging more into a larger watercourse that can dilute some of the flow, some of the water concentrations that are discharged. And so source is helping us understand what happens in the waterway with those concentrations. And we're miles from Sydney. This is down near the Warragamba Dam. And so really in that peri-urban environment that provides a few opportunities for doing different integrated water management solutions, which is exciting. And in terms of contours, these are the sort of inputs that we drew into the source model to do the delineation of catchments and really try to do a better model with more detail from the contours available for this project than we'd used in broader catchment modelling tasks before. And we get down to scenarios of trying to consider these different discharge locations and some reuse, expanding reuse onto nearby farms. That's the scenarios that we're assessing. with different water quality locations that we've been monitoring upstream of our 2 discharge locations that we've calibrated against and used as inputs to the model in the case for the Nepean. And so the source model, if you can see this schematic now, shows our inflows to our sewage treatment plant. So we've been able to simulate that flow and some variability. We're using an hourly model, so got a range of characteristics in there and the treatment performance, simulating the storage of that water in 2 different dam locations and reuse from those dams, as well as an off-site dam, so a transfer rate off to those nearby farms and different irrigation demands off that off-site area. And then different water quality performance and discharge into waterways. And the Stone Quarry Creek catchment we simulated with the runoff from the catchment in terms of the source model capability there. With the Nepean, we just simulated a gauged flow monitoring gauge location as an input to the model at that point. But in the future, we could refine that, drawing on another model that's being developed now. So the sort of outputs that we've been looking at, we're using 28 or 29 years of data. So we're representing a whole range of variability in conditions and able to show how that variability influences the volumes of water that are discharged year to year. And that's certainly something we're thinking about with the challenges of licensing something that in a wet year might be a whole lot more discharged to waterways, and in a dry year with the opportunity to reuse more allows you to minimise discharge to a much greater extent. So we consider different amounts of reuse and what that means for the volumes of water expected to be discharged. And then we narrowed our focus for an environmental approval process that's going on now. So we've got documents in the public domain that are seeking stakeholder feedback on these different options, trying to compare a baseline of just under 3 megalitres per day coming into the treatment plant and our current discharge. So that sort of top line, the scenario 1 is our baseline condition. Then looking at 3 scenarios where we have improved treatment, with 2 of those being with additional reuse, and the third one with no additional reuse. So we end up with different volumes of water discharged in a typical year, and we've got 2 different locations that we're looking at for discharge, either the same location that we're discharging now in Stone Quarry Creek, or discharging to the larger waterway with the Nepean River. And so our output kind of graphics, we've characterised the change in total nitrogen concentrations upstream and downstream of our discharge location. So for the different scenarios, a median and a mean concentration, and tried to understand what might be changing for each of these and what sort of magnitude we might expect in the change from upstream to downstream, and for these different scenarios at the downstream location. And we present some annual data as well with the 2 different scenarios, looking at the median load for each of those scenarios with those red lines, and the year by year for the annual TN loads discharged. Then similarly looking at the comparison of the differences in the TN concentration upstream and downstream, and ranking those differences to see how much we're seeing an increase and how big that increase is as well. And then with discharge to 2 different locations, it's been really useful to compare the outcomes at the downstream location, so downstream of the confluence where those 2 waterways come together. So that provides a nice way to compare all of the scenarios against one another. Comparing each of the scenarios and the small magnitude of increase that we see with those scenarios to help people compare each of them. selecting the metrics was quite an interesting task. So because we're comparing scenarios of discharging to small watercourses and to large watercourses, there's different metrics that highlight the pros and cons of each of those approaches. And so the proportion of the discharge as a proportion of the creek or river flow is certainly a metric that, indicates something more positive for the larger river system in terms of the discharge being a relatively small proportion, and equally the number of days of discharge and those type of metrics have been useful to characterise. But we were playing with, it was a challenging task to try and find metrics that were able to communicate most clearly the advantages and contrasting aspects of each of these scenarios, particularly with different things moving in different directions. But it does highlight the trade-offs that need to be made in these circumstances, and the various aspects. The various limitations was something that was quite important for us to understand and communicate with those who were interested in understanding the model and understanding what the model could tell us and where the limitations are in the capability of the model. So gauge data is certainly something that has been an issue in the past in terms of having confidence in the different gauge data that's available. And so that's, spending the time making sure that that data is as good as we can get it, and where needed that, new infrastructure is put in to make sure that the data that we want to rely on for the outcomes of the modelling, lower flow conditions or, periods where sufficiently good data, have confidence in your calibration and validation sort of phases is really important. So we're trying to focus on that into the future to make sure that we can have that data to refine the modelling, the capabilities of the modelling in that sense. Similarly, water quality data, where we're wanting to move to understand bioavailable nutrients, we really do need to have sufficient data to characterise what trends we're seeing in different seasons, and really be able to have that information to help guide what the model can be used for, and those relationships that we want to then simulate. And the last aspect is linked to those, I guess, but the question around choosing to represent aspects in the model with simplicity, so that you can talk about with clarity various assumptions that are critical in the modelling. So things like a nitrogen discharge concentration. If in various phases we chose to use just a simple metric a simple assumption in order to have that clarity. So selecting a single concentration as the discharge that is simulated in the model. And then at other times, it's better to have the complexity with a distribution that allows you then to see the statistical analysis that reflects what you might see in reality in terms of waterway outcomes. And it's certainly a difficult balance, because if you go with a distribution for concentrations of nitrogen or other parameters in the discharge, needing to have that data to justify the relationships that are established is something that is often lacking in some ways, to have good confidence in what you're representing. And then when you go with something more simplistic, to be able to say with confidence that you've not underestimated those concentrations at different times or at critical parts of the model, then it does leave you with a situation where, when you're representing some of the modelling outputs with statistical tools, the modelling results look a little bit flat, in the sense that they don't represent that variability, and so a little bit potentially not representing the full range of concentration and experience that the waterway will see. So it's been a really interesting project for us, and really helpful, I think, for us to understand where the source modelling tool can help inform waterway and wastewater management, and equally moving into those tools that eWater are developing and refining, with adding in the plugins for Music X and also for urban developers. Really useful, I think, as we start to think about integrated water management solutions more, and have these tools to really characterise with clear metrics what the benefits are of different integrated water management solutions, and link that to economic benefits for adopting those type of solutions, and having that confidence in the costs and benefits of the various solutions. So really important tool for planning, and important to be able to do in the most efficient way. So welcome any questions if you want to in those aspects.
Thank you, Emma. I agree. That is really quite a novel way of starting to think about an integrated approach, and those extra additions will be fantastic. We do have a question, probably from someone you know well, Marlene van der Sturen from WaterNSW Wales. Marlene says, nice preso. Have you looked at the changes in concentration in relation to the different flow regimes? For example, low flow tends to have a higher increase in concentration than a high flow.
Yeah, so we've certainly started to drill into a lot of that more, the breakdown in those different flow regimes in a more detailed report that we're developing up now, and using a few other methods as well to characterise that. So we've got the source model, but also some generalised linear models that have been developed off the monitoring data itself. So a range of tools to try and help us characterise the various things we're seeing. And yeah, certainly the concerns in low flow are exactly why we're in a challenging position in trying to secure approvals to expand discharge.
Definitely. Well, thank you, Emma, and perfect timing as well. So that's congrats from me. All right, so yeah, if you've got more questions, then feel free to grab Emma in the break.
Excellent.
So we're now going to change tact a little bit, and I'm going to invite Helen Fairweather from the University of the Sunshine Coast to the stage. And Helen is going to share some insights into how we might be able to use Lagrangian, hopefully I pronounced that right, data. Is it the next frontier in river modelling? So welcome, hopefully, to the stage, Helen.
Okay, can you hear me?
Yes, we can.
Terrific. Can you see me?
I can see you.
Great. So let me get the PowerPoint going and we'll get started. So I feel I'm not going to be talking about source modeling. So hopefully
Data's always the next frontier.
That's right. Well, I will mention it, I guess. So now let me see where I can share my screen. There we go. Bear with me. This is not.
It does need to be open in the background.
Yep, got it. Got it. Bear with me one. Okay. Hopefully you can see the screen. That looks like it's all working.
I can see and leave you to it.
You can see I'm in my cupboard here. So good afternoon, everybody, and thank you for the opportunity to present. I noticed there's quite a number of participants, and went through the names, and there's some people from that I knew in past lives. So hello to those that I knew previously when I was new in New South Wales. I'm now in Queensland at the University of the Sunshine Coast. So what I'm going to be talking about is some research that we've been doing over the last probably 5 years. And this research I've been doing in collaboration with QUT, Professor Richard Brown and Dr. Kabir Siwara, mainly from QUT, and a range of students from both QUT and USC, both honours and PhD students. So I acknowledge the work that those students in particular have done, and I've grabbed some of the output from that to present here today. So I'm by no means claiming credit for all this material that I'm going to present. And I also like to thank Trudy and eWater for providing this opportunity, because I think it's a great, way for us to share knowledge these days, and I've certainly found the afternoon to be very informative thus far. So what's Lagrangian data? So Lagrangian essentially is data collected in time and space versus the Eulerian data, which is the fixed measurements that we're more familiar with from things like gauging stations, or the image here, an ADV, an acoustic Doppler velocimeter. The Lagrangian data that we're collecting, so you can collect it using a number of methods. DIES is a typical method that was used previously, but we've developed these drifters based on the drifters that they use in the ocean. So we've developed drifters for shallow waterways, mainly for rivers and estuaries, and that's where we've been doing most of the work over the last 5 or so years. So the spatial characteristic is dynamic when you're using Lagrangian data, because one of the central elements of the drifter is a GPS unit. So these drifters, this one here, these are just probably 50 millimeter PVC tubes that are weighted so that the top of the tube extends just a little bit out of the water, and it just has a GPS unit in there. So we deploy those drifters typically in flocks of 3 or 4, generally 4, and that enables us to then collect dispersion data, and that gives us an inference of some water quality, as well as the velocity of the drifter as it moves. These cheap ones we can put together for under $100, and we do them in different lengths so that we can get a representation of the velocity at different depths as well. That one in the middle there is a high quality drifter, and it uses a GNSS, so we get more accurate measurements in that drifter. So they're the drifters we were using initially with QUT, and we just had a GPS or a GNSS in them, and we deploy them and collect the data and have a look at how we would use them in modeling. So how is it collected? Well, since those pictures that I've showed you, we've also now developed it further so that we also have put in some water quality sensors into them. Now, these are some images of 2 student projects that's happened over the last 3 or 4 years. I have another student who's also taken the development even further than what these show. So these drifters they still just have a GPS unit in them. They don't have the GNSS, but as I said, they have the water quality sensors. So they're generally about 100 millimeters in diameter, stand about 54 centimeters high. The top section is waterproofed because it contains all the instrumentation and the microprocessor. We're using, at the moment, all these previous ones used a Raspberry Pi. We are, I think, moving towards an Arduino, so a microcontroller, just because the battery power was a bit of a draw on the Raspberry Pi. And in fact, in this one, we had, I think, both the Raspberry Pi and the Arduino. I don't know if you're familiar with that technology. But a Raspberry Pi is essentially a microcontroller, and an Arduino, sorry, Raspberry Pi is a microprocessor and is essentially a mini computer, a Linux-based computer, and the Arduino is a microcontroller. And so you don't have a screen interface to it like you do with the Raspberry Pi. So these sensors that I showed here, turbidity sensor, temperature, dissolved oxygen, EC, and pH, were all installed in this part here in the first sensor, in the first drifter that we incorporated the water quality into. And you can see that you've got holes for the water to flow through there. Now, this design was okay for doing some research, I guess, but ultimately we want these devices deployed on a regular basis and ultimately by local council. So I should say I think I mentioned I'm at the University of the Sunshine Coast. This research was also done in collaboration with the Sunshine Coast Council. And in fact, it's been funded by an ARC linkage grant, and the Sunshine Coast Council were a partner in that research grant and provided a cash injection to it. So I must thank them for that. So ultimately, the idea is that we have these drifters deployed on a regular basis, and we get a picture of water quality and also flow throughout a system. Now, and then we can incorporate some modeling into that. So this was the second last version, this one here. And we had some difficulties with the waterproofing. So this version here had this screw top, and it was really problematic when you unscrewed it and all these wires fell out and things popped out, and it was a mess. So we reconfigured it, and so we just had push buttons on here. The idea was you'd just be able to turn them on and off you go. We send the data up to ThingSpeak, and I'll show you some output of that in a moment. That this was a little problematic. We did actually lose 2 of these. These ones cost about 100. The new versions are going to be a little bit more than that, but they won't sync, which was this was a really a big problem. Now the way that the data goes up to ThingSpeak at the moment is we have a SIM card, essentially just a phone card in there, and we connect to ThingSpeak. If it can't get that connection, it uses the hard drive capacity of the Raspberry Pi to collect the data, and then when it can connect again, it uploads it. So we've done research around various areas across the Sunshine Coast. This is the Curramundi Lake, which is an ICOL, an intermittently closing and open lagoon. And the Sunshine Coast Council actually closed this lagoon on a fairly regular basis as a means of midge control. I don't know if anybody's ever come up to Sunshine Coast, but midges can be horrendous. And cause quite a bit of problem if you're being attacked by them. And the Sunshine Coast Council is very progressive and don't like to be spraying chemicals all over the place. So they implemented this control where they essentially drown the larvae. So they close this opening here, and that raises the water level, because there's water obviously coming down from the base flow if it hasn't rained, and then and then that just they have it submerged for about a 6-week period, and that kills the larvae. But that gives us a great opportunity to do a whole lot of research with the drifters, which we did over several years. When we're deploying the drifters, it's because of their profile. It's really important that we get wind speed as well. So when we go out on a campaign, we generally install the drifters, install equipment like the anemometer there, an ADV, and we deploy the drifters over a period of about 48 hours so that we get all the tidal data and the changes having in the system. And generally we do it on a king tide as well. The other area that we've done some work is in the Pelican Waters Canal estate. and also down here in Bell's River or Bell's Creek down through there as well. So I'll show you some data from each of those in a second. We've also done some water in the passage itself. I don't have any data from this campaign, but we deployed the drifters in the northern part of the passage and the southern part of the passage at the same time. So we were able to get 2 teams, and that was really quite an interesting experiment. So this is just a picture of some of the data that we collected. This is just the track of these 4 drifters in this case, in the different colors. And you can see that they stay pretty close together. They're deployed here. Whoops, sorry, go back. They're deployed here at the start, and over time they start to disperse. So we can then calculate a dispersion coefficient from that. We also, now that we've got the water quality parameters in the drifter itself, we're also deploying a water quality measurement in situ or Eulerian measurement as well, so that we can do some comparisons. And these are just some of the data that goes up to ThingSpeak. So this is in real time. You can see this data in real time as the drifter is being deployed in the system. So this is the dissolved oxygen, this is the pH, this is turbidity of drifter 2, and this is the temperature of drifter 2. They're all for drifter 2 there. So how does it compare to that Eulerian data that I mentioned? We've done quite a few comparison exercises, if you like, both on the water quality side and on the flow side. So of course, one of the problems with doing comparison is you've got a piece of a device doing the measurements in situ, and then you have the drifter coming down alongside it. So you have to set some parameter for capturing the speed of the drifter over a restrained area, and the proximity to, in this case, the ADV. Now, for this one, it wasn't so good, the comparison, and that's because none of the drifters went close enough to the ADV to give us a reasonable picture. This one was another one. This comes from a paper that I was co-author on by one of the PhD students, Nida Madani, and you can see that this is the ADV measurement. This is the water level. And these are the drifter, an aggregation of all the drifters that were in proximity to within a certain boundary to the ADV at that point in time. And you can see it's not fantastic, but we do have a little bit of work to do on improving that and getting more data to really see what's happening. This is the WASP model output from. Oh, no, sorry, beg your pardon. This is comparing the fixed water quality sensor, so for our pH, and the average drifter pH as it went down the river in close proximity, so just the one drifter in this case, and that's approximating the direction anyway. One of the really nice things about putting it up on ThingSpeak is you can get this map, and you can animate this to show how, in this case, the dissolved oxygen changes as the drifter moves down that river to the mouth. So, incorporating it into river modelling, we have incorporated the water quality stuff. One of the honours students did a WASP model and looked at how, in this case, the dissolved oxygen compared at a downstream location X to the Lagrangian data. Now, obviously, that has some challenges as well, because you need to be able to have the data from the model at that same location as your output from your model. So there's some challenges there. This is from Delft 3D, and we're using or investigating the use of OpenDA, Open Data Assimilation, for bringing in the Lagrangian data. So this is again the Karamundi Lake, and this is again the work that Nida Madani did for her PhD. And up here is where we deployed the ADV to get some upstream boundary conditions. We've got a Sunshine Coast Council engaging station here. We've set the boundary, the downstream boundary with the lake closed. So that gave us a fairly good way to do the calibration. And then we can have a look at the comparisons of the observed versus the simulated velocity in this case from Delta 3D, and you can see that it's not too bad. So that's just for one trajectory, and this is for over a much larger area. So essentially, the Lagrangian measurement, the Lagrangian velocity, comes from following a parcel of water down the river system. So your drifter is mimicking that parcel of water, and I think it's the future in terms of that's the end of the presentation. That's the future in terms of modeling, and what I'm really keen to do now is to investigate how we can bring in that the drifter data into the source modeling. I've not until a couple of days ago I've not used source before, but we eWater, I think it's been eWater, have been really helpful in getting some of our students involved and offering a course over the next little while, or an exercise that we'll be involved in, myself and my students, to see if I can incorporate it into my teaching, essentially. So that's really all I wanted to cover in this presentation, and I'd be keen to answer any questions that anybody might have.
Thank you, Helen. Oh, I'll just check. Okay. So I've got to look in several places for my questions. I will just pass on a comment from our Chief Executive, Robert Carr, to say that Source, he's going to really test me now. Source has both an Eulerian and Lagrangian module for tracking of salinity and water quality. So there's definitely opportunities to use Source.
Oh, that's great. Yeah, okay. I'm really keen to investigate that.
So a question that's just come through that might relate to where I was heading with my question. What velocities do you need as a minimum to move them?
Yeah, look, and that depends on the size of them. It doesn't take much. Well, it depends on the size and also the wind conditions. The wind conditions are really important in terms of how they move, and we need to measure the wind when we're deploying these to ensure that we're correcting for it. My answer, I'm sorry, is it depends, but it doesn't take a lot. As you could see in some of those data, down to 0.05 meters per second, we're able to calculate, or less than 0.05 meters per second.
Sure. So there's another question from Angus Dyson. Angus asks, is there any evidence that following the particles allows for measures that correlate better with stream ecology?
Oh, look, that's a great question. And one of the really, just from a monitoring point of view, one of the really great advantages of drifters is that you're able to detect source pollution, point pollution, and diffuse pollution. So because it's going down the river and all of a sudden your turbidity jumps up, you can pinpoint exactly where that's coming from. So I think from that point of view, that's a really important thing for correlating better with stream ecology, just from a monitoring point of view, not even taking into account the modelling.
Yeah. Well, in the absence of another question, I will ask mine. I guess perhaps it's related to other maximum velocities, but tomorrow in the technical session, we will share some of the work we've done to support the Murray-Darling Basin Authority develop a source operational model for the River Murray. So that's a pretty complex system where real-time data can be pretty useful for efficient operations. How would it go in such a dynamic environment as that?
Well, that's my plan. That's my next plan, and I've been grappling with where we run the model, and I think what we'll be doing is running the model, and then whatever modeling we end up incorporating into the system. Initially, I thought I'd run it on the Raspberry Pi as it was moving down the river, but I think that's just too. The Pi is just too limited for that. So my thinking is that we run it in the cloud in real time as it ingests the model, the data that's collected as it's moving down the river. And that's ultimately what we were looking to do, because as you know, the gauging stations is the data that the data from the gauging stations is what you really rely on for your flood modeling. And when the peaks are and the data, I'll take one step back. The data uncertainty is the greatest at those peak flows, and certainly that comes about from the condition of the gauging station and something that might happen to it, but also then the stage discharge curve or the rating curve and the uncertainty around that. So the deploying these in a flood situation is something we're really keen to do as well.
Excellent. So lastly, a question from Michael Finger from the Victorian Department of DELP. Do you think they can scale to smaller waterways and very shallow streams?
Yeah, look, I think there are some problems with it because they get hung up if they're, and you need some depth to them. So, well, I'm not sure what Michael is referring to in terms of very shallow, but we did have some issues with them, particularly if they moved over to the banks and they'd get hung up, and then we'd have to pick them up and move them. That's fine. But in terms of, well, and we're thinking about some modifications to them so that be, maybe a little propeller on them that shoots them back out to the middle of the river if they get stuck, or something like that. So look, I'm not sure at the moment. Probably a metre of water is probably the minimum that you'd want to deploy them in.
Mm-hmm. Excellent. Thank you very much, Helen. Please grab Helen on the floor if you've got some more detailed questions for her.
Thanks, Trudy.
My pleasure.
So how do
you
send me
go away? That's fine.
Oh, so Martin said he wants to. It'd be great to track tidal changes in Adelaide River. Yeah, get in contact, Martin.
Cool. All right. Thank you.
My pleasure.
Excellent. Well, that brings us to the conclusion of our formal presentations today. As I indicated several times, we've deliberately created lots of breaks for networking. So for the next half hour, 45 minutes, we're just going to leave the session open. If you would like to stay and keep talking, chatting with your friends, meeting new people, sitting with one of our presenters and asking them some more detailed questions, then please do so. Otherwise, please join us again tomorrow afternoon from 1 o'clock, where we will have two sessions. One, again, focusing on a broad range of things happening in the Australian space, and then a second special session where we have invited some speakers from the Mekong region to share some of the things that they have been doing, particularly with source, but also some broader decision support modelling. Before I run away, I also want to put a shout out that tomorrow afternoon we're having a technical Q&A session where we will share some of the enhancements on the source platform and music element developer in the last little while, but we absolutely want to take your questions. So to help us prepare, if you would like to send me a direct message today or email me overnight, then please do so, and I will get our developers to answer them tomorrow. So thank you. Grab yourself a cup of tea or something else, depending on what time of day it is where you are, and go and network.